much of that work going on right here, as we just saw as we walked around.
That's right. This is a place with sort of much of the key history of American telescope building, and it's appropriate then that we're at the center, or at least playing a crucial role in the development of the Giant Magellan Telescope. The original large reflectors on Mount Wilson were all designed and built here. Much of the early work on the Palomar concept was done here. And the key observations of the expansion of the universe, the scale of the Milky Way galaxy, were done here. So it's not just Hubble, but it was Hubble, Baade, Shapley. This was the core of American astronomy in the previous century, and we're hoping it's going to continue to be one of the key players in global astronomy in the next century. And the Giant Magellan Telescope is an essential part of that plan. So it's important for Carnegie, it's important for our domestic and international partners, and people here at Carnegie are thrilled that we're playing a vital role in that project.
Talk about where the project is now. I mean, it's only been in, a couple of weeks, maybe slightly more, that you announced another major partner.
That's right. We were very pleased that the University of Chicago joined the project recently, and there's some interesting history there as well, of course. Hale came to Pasadena from the University of Chicago, where he had built the Yerkes 40-inch refractor, had designed and begun his early reflector projects. In fact, he brought that concept and some of the money with him from Yerkes to build the 60-inch at Mount Wilson. So it's sort of like an old family member now that you've reunited with. So we're thrilled to have Chicago part of it. They're a very strong group. They have a very strong astronomy and a good, very strong physics department, and that brings a lot to the project. So we're thrilled to have them join us. And we think that we really built a partnership that's very strong. Domestically, we have many of the key and prominent U.S. universities, but having our international partners in Australia and Korea is essential as well. Australia has a really long and proud tradition of astronomy, and they're known for doing an awful lot of science on relatively few resources, and that's just that kind of spirit we want to bring to the GMT.
What's special about the GMT?
Well, in a generic sense, you gain two things by building a very large telescope. You win by collecting more light, because as astronomers we always want more light, whether we're dividing it into finer wavelengths or looking in greater detail, looking fainter, which in some sense allows us to look further away, but often just allows us to look for objects that are intrinsically less luminous. So the collecting area is a big gain, and you win by the square of the diameter in that case. So when you double the telescope, you get 4 times as much light. The GMT has 10 times the collecting area of our 6.5-meter telescopes at Las Campanas in Chile. That's what Carnegie's principal facility is. So that's a big gain. A factor of 10 in sensitivity or a factor of 10 in collecting area, that's a huge step forward. But there's another dimension as well. That is, as you increase the aperture of the telescope, you improve the angular resolution. And that depends simply on the number of wavelengths of light across the aperture. So as the aperture goes up, you collect more wavelengths, you get finer angular resolution, provided you can defeat the blurring impact of the atmosphere. That is, you go outside on a summer day and you look along a warm stretch of pavement, you can see the images shimmer. That's due to turbulence and heat rising in the atmosphere, particularly rising off the pavement. But that phenomenon exists throughout the atmosphere, and it limits the resolution of the telescope. Once the aperture gets above about 20 inches or even less, about 12 inches, the resolution is completely limited by the atmosphere. In the past decade or so, and really in sort of the past 5 years, people have fielded so-called adaptive optics instruments that allow you to measure the distortions in the wavefront, that is the incoming light caused by the atmosphere, and cancel them out, much in the same way as your noise-canceling headphones measure the noise around you, put in a signal that's the exact opposite of those, and phase-cancel them. We're phase-canceling the distortions in the atmosphere by modifying the shape of a deformable mirror on very short time scales.
In 1 minute, much more about the Giant Magellan Telescope from Project Director Patrick McCarthy. This is Planetary Radio.
I'm Sally Ride. After becoming the first American woman in space, I dedicated myself to supporting space exploration and the education and inspiration of our youth. That's why I formed Sally Ride Science, and that's why I support the Planetary Society. The Society works with space agencies around the world and gets people directly involved with real space missions. It takes a lot to create exciting projects like the first solar sail, informative publications like an award-winning magazine, and many other outreach efforts like this radio show. Help make space exploration and inspiration happen. Here's how you can join us.
You can learn more about the Planetary Society at our website, planetary.org/radio, or by calling 1-800-9-WORLDS. Planetary Radio listeners who aren't yet members can join and receive a Planetary Radio t-shirt. Members receive the internationally acclaimed Planetary Report magazine. That's planetary.org/radio. The Planetary Society, exploring new worlds.
Welcome back to Planetary Radio. I'm Matt Kaplan. We are visiting with the director of the giant Magellan Telescope, Patrick McCarthy. I invite you to visit our show page from planetary.org to hear my complete conversation with Pat and to accompany us on a fascinating, nearly 15-minute audio tour of the Carnegie Institution facility in Pasadena, built in 1913 by George Ellery Hale. That's where the $700 million GMT project is managed. For now, we'll rejoin Pat in the Carnegie Library under Hale's portrait. Everybody gets caught up, of course, in the mirror, because size matters. What about the other end of the telescope, the instruments? Have we seen the same kind of evolution with the instruments that actually deliver the images and science to us?
Very much. In essence, the real gains in sensitivity that telescopes have seen in the last 20 years or so have come from two areas, primarily cleaning up the thermal atmosphere or the thermal environment in the dome to make sure the telescopes deliver the best images, but primarily from improving the instrumentation. Going from early days of photographic films that had a sensitivity of about 1%, that is 99% of the light that fell on the photographic plate was lost. They were inherently nonlinear, that is, you couldn't really derive quantitative information from them. So with the advent of linear detectors, digital detectors that have high quantum sensitivity, really have improved the gains and sensitivities of telescopes. And now, as we start talking about extremely large telescopes, the instruments themselves take on a scale, complexity, and cost that are comparable to the previous generation of telescopes. That is, the scale of an instrument from GMT will be on the order of that of the telescopes that we built in the 4, 6, and 8 meter era. So they're going to be technically very challenging, but they're the key to analyzing that light that we've collected and fed to the focal plane, but all the real scientific work happens inside the instruments.
So much of a project like this, as George Hale learned in his day, is not so much science as inspiration and fundraising. Big challenge, right? I mean, I think you're now at about 35% of your goal that you'll need to put this instrument on that mountain in Chile.
That's right. The technical challenges are very real and very serious, but they are tractable, and we have convinced ourselves that there are no fundamental technical limitations to building the telescope. The real challenge is, as you say, it's finding the money, and that means inspiring people, whether it be philanthropists who are interested in supporting this, the general public who might wish to support this through public funding, and just raising enough awareness and excitement about it that it becomes sort of a self-generating proposition. As you say, we have identified or secured 35% of the funding, but I should clarify that in the sense that we have partners whose goals and intentions bring us to 100% of the total funding. The 35% refers to commitments that are in essence in the bank that we can draw checks against. So we're very confident that we will grow that 35% to 100%. That's the intention of the partners. They're making every effort to raise that funding. So we're being very conservative about where we talk about the funding level. And I think the prospects of us getting there to 100% are very, very good now.
Well, that makes sense. If they're in with tens of millions of dollars already, you'd think that they probably intend to see this through.
Yes. For example, the partners didn't sign up and didn't have their university president sign without the intention of actually making this a success. There's just a level of when their business offices will allow that money to be drawn on. And that's where this $250 million figure comes from, is a 35%. And we hope to get to roughly our $650, $700 million figure shortly when we begin construction in probably sometime in early or mid-2012.
Really, I guess it's sort of a family of telescopes of this class coming online that are so much more powerful than anything that currently exists. It's easy to say that we've been in the golden age of astronomy. I don't know, are we headed toward a platinum age or a diamond age?
Well, as I tell people, there's never been a better time to be a young astronomer, and I really wish that I was one again, because the future in terms of the potential for new discoveries, new technical capabilities has never been better. As you mentioned, there's a new family of what we call extremely large telescopes coming along, one based in Europe, two based here in North America. But in addition, there are new facilities coming along in space, the James Webb Space Telescope. And in the millimeter and centimeter wave astronomy, the U.S., Europe, and Canada are about to commission the next generation very large millimeter wave observatory in Chile, and that's going to open a whole new world of studying star formation, planet formation, anything that's cold or embedded in dust and cold gas. That ALMA, Atacama Large Millimeter